Hey everyone. So in this video, you'll notice that I forgot to put the brackets around the ion. So sulfate, it carries a charge of -2, and so our formal charge math is showing us that. We've memorized that from years past. I just forgot to do that. It's something that I tend to forget to do. Shout out to one of my students today who I forgot in class when I was doing this particular example. I forgot to once again put the brackets around that. So shout out to you, Allie. Good job. I appreciate that. So kudos. So don't forget that. So give credit where credit is due. That's one of those things I tend to forget. So I always enjoy it if somebody can, if you can catch that, that means you're learning. That means you're doing something. So I try to make these videos, as perfect as possible. That's why I do a lot of editing of it. But sometimes I miss that detail. So, and it wasn't even in my mind that I forgot to put those brackets. So I would have gone to edit this video and would have went, well, crap, forgot to put brackets. So I would have had to do something. So since I have an opportunity, I wanted to reach out. Let's get back to the lesson video. Good job once again. I appreciate you pointing that out. Don't forget the brackets if it's an ion. Bye. Hello and welcome back. We're going to jump into what I'm titling Octet Rule Breakers. In other words, if you've watched the previous lessons on this type of material, we're looking at VSEPR theory, we're looking at molecular bonding, we're looking at how covalent bonds interact back and forth, polarity, things of that nature. We have found that we've talked about formal charge. So if you haven't, if you're unsure what I'm talking about, you're going to want to take a look at some of these videos that I have linked here for you, and that will help out, and then come back to this video. So octet rule breakers. So we know essentially we're looking for molecules or with atoms, this concept of the rule of 8, right? So, the whole octet thing means 8, right? So if we have 8 electrons, with the exception being hydrogen or helium, because they're in group 1, right? They're in period 1. Not group 1, period 1. Then, that's just like a duet rule, right? It's just 2 electrons in that first orbital. So octet rule breakers, usually with this, what's going to happen is more than 8 can show up around 1 electron, or less than 8. And there's a couple of examples of each. So in this video, I'm going to dedicate it to just one example, and then I'll have another lesson where I sort of expand out and look at some other examples. It can be a little detailed, and so I just want to focus. I was going to say hyper focus. I just want to focus on just one example in this video, and then I'll do some other videos. So let's just jump in. So octet rule breaker. Let's look at something like a sulfate ion. So we know when we're done with this, we should have 1 sulfur, 4 oxygens, and the formal charge on all of it should calculate out to be a -2 charge, right? It's essentially a molecule that's still carrying a charge, which is why we call it an ion. Oh, that morning pick me up. I love that stuff. So if we follow rule 1, 2, and 3, right? So if we were to follow all the rules, 4 oxygens, sulfur, there's one of those that's 6 electrons. The oxygen, there's 4 of those, that's 6 electrons, and then we have to add in the other 2 here, right? And so when we're done, we know we need a total of 32 valence electrons, right? If you're not sure how to calculate that, jump back into those other videos where I detail that for you. So 32 electrons. So rule 2, we know, and rule 2 and 3 is basically bond it together, and then let's just complete it with lone pairs and see what happens until we satisfy our octet. And so if we were to do this right here, and then satisfy the octet around all of each of these oxygens, right? If we do that, we get 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We got the octet rule satisfied around every atom. This looks good. This looks good right here. But wait, there's more. It's not good. The reason it's not good has everything to do with formal charge. And so you're going to want to go back, watch that video on formal charge. But if we were to calculate out formal charge for each of these, we would look at the formal charge on the sulfur, and then we would look at the formal charge on the oxygen atoms, right? And so remember formal charge, so the group number, sulfur is in group 6, minus the number of electrons that are in lone pairs, that's 0, minus 1/2 the electrons that are in bonds, so that would be the 2, 4, 6, 8, right? Because there's 4 bonds on this one, so that's 8, right? So 6 minus 4 equals 2. So if we look at this, that means this sulfur is carrying a 2+ charge. Oxygen, group 6, minus the number of electrons in lone pairs. All these oxygens are bonded the same and have the same amount of valence lone pairs on them. So the math is going to work out the same for all of them. So I'm going to calculate it once, and we can assume that all 4 of these have this. So the number of electrons that are in lone pairs, that's 2, 4, that's 6, minus 1/2 the number of electrons that are in bonds, and that would be the 2. So the 6 minus 6 is 0, minus half of 2, so minus 1. And that kind of makes sense mathematically, because if we were to, by process of, I don't know, elimination for lack of better words, I guess, I don't know. But so here's a negative, here's a positive 2, so those 2 negatives and that positive cancel each other out, and so we can see that right here, there's still an overall net of -2, which matches up to that. So this looks good. So far, there doesn't seem to be a problem. But there's a problem. The problem is there are too many atoms carrying charges that are a wide range from 0. We've learned in previous lessons that formal charge, we want as many atoms as possible to be carrying as low a charge as possible. I'll be right back. So for these atoms to carry as low a charge as possible, there's going to have to be some bonding that is done a bit differently. So let me move this out of the way. I'm going to leave this here so that we can see it and compare. All right. So essentially now what we've got is we've got to think, how do we bond it differently? Well, the only way to bond it differently is to start thinking of doubling up bonds, right? To start double bond things. Well, if we do that, we go, wait a minute, but that breaks the octet rule. Because if we do that, now we've got 2, 4, 6, 8, 10 around sulfur, but we're supposed to only have 8. Well, the whole theme of this lesson is that we're breaking the octet rule. So right now we've got 10. So we ask ourselves, would something like this, would this work? Well, we can, let's take a look. So if we do this, we've got this here, and then we've got the octet rule that we need to complete, right? And so this gives us 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. All right, so we have 32 electrons. All right. So the question is if we do this, what's our formal charge going to be? All right, well, let's look at this right now. If we look at the formal charge on the sulfur, then we've got group 6 minus the number of electrons in lone pairs, still 0, minus 1/2 the number of electrons that are in bonds. And so we get 2, 4, 6, 8. Now we have 10, right? So half of 10 is 5. So that would give us a, 6 minus 5? That's a positive 1, right? So that gives us a positive charge here. All right, well, so far that brought down the positive charge a little bit. That's looking kind of good, right? So let's look at else what we've got here. All right. Formal charge on the oxygen. All right, so if we go formal charge on the oxygen, so here we have 3 that are single bonded. Now we know from our previous math from up here that the single bonded ones, they're going to carry a negative charge. All right, I guess I should have written it on the other side. And I didn't change it to yellow. Sorry about that. So they're carrying a negative charge. Well, all right, so I'll be consistent. I'll put that in yellow. I want to be consistent. So there's a negative charge, there's a negative charge, and there's a negative charge. That's nice contrast. I like that. So right here, we look at this, and there is this positive charge here and a negative charge here. I just picked the first negative charge closest to where my pin was. Those would cancel each other out. There's a net of -2. Well, let's see if this works itself out here. So let's do the formal charge on the double bonded oxygen, all right? So right now, this is going to be for the double bonded oxygen, all right? dB, not decibel, double bonded. So group number 6, that doesn't change, it's the same atom. Number of electrons in lone pairs, hey, we have 4 now, minus half the number of electrons that are in bonds, that's 2, 4. So 6 minus 4 is 2, half of 4 is 2, that gives us a 0. There's no charge. So here's what we've got for this. So far, this looks pretty good. But wait, there's more. Let's, in the spirit of formal charge, let's see if we can get the charges even lower and still get a net of 2, which means, is there a way to get rid of the positive charge on the sulfur, and is there a way to get rid of one more negative charge? The only way to know is for us to experiment here, all right? And the only way to do that, what we want to do is just experiment. Let's add another double bond. Again, we're breaking the octet rule, so far, so good. All right, so now let's fill out the octet. And then we know this would be this would be this, and over here we would have this, right? So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Still have 32 electrons. So now we can back up, and what we can do is we can take a look at what we've got. Our single bonded oxygens, we know are going to carry a negative charge. We know this from the previous math that we've done earlier. So I'm just going to put a negative charge here, and I'll put a negative charge here. If you look over there on this example, we see that the double bonded oxygen that we just calculated, it carries no charge. So I can leave both double bonded oxygens with 0 charge. So the real question is what's the formal charge of this sulfur right now? Have we brought it down to where it stays 0? All right, so group number 6 minus 1, oh, I'm sorry, I jumped ahead of myself. Minus the number of electrons in lone pairs, that's 0. Minus the number of 1/2 the electrons in bonds, right? So that is, right now we see that is 2, 4, 6, 8, 10, 12, right? So you can see where we're going with this. I think so, right? So that is 12. What's half of 12? 6. 6 minus 0 minus 6 is 0. So so that means we take a look at this. Oops. That means that this right there, that is the most favorable structure. It is, oops, wow, I forgot I had the geometric lock on. Let me take that off. So this right here would be our most favorable species. All right, and we've talked about that in class. That's our most favorable species. So this is the least favorable, and so is this one, least favorable. The most favorable is the one that still carries the proper charge, whether that charge is 0, -2, +1, it doesn't matter what it is. And as many atoms as possible are as close to 0 as possible. The range of formal charge values is as low as possible. So you think of a number line, 0 in the middle, right? you want the range of those numbers to be as little as possible. In the first example, we had +2, and then we had -1. And that's really a range of 3 if you think about it. We had, on the next one, we had a +1 and a -1. Well, that's pretty good. That's pretty good. That decreased it, but we have a lot more that are still negative. The question is could we bring those charges down and still keep our net charge of -2? And we were able to do that by adding a second double bond to that central atom. Okay, so it's trial and error. I mean, there are some rules that you can follow. I've put those rules in the description to help you out, and on multiple lessons I'll highlight different examples of those rules. Essentially, like things, hydrogen and helium, they follow the duet rule. That breaks the octet rule. We just saw that sulfur can have, this is what we call an expanded octet. All right, this is an expanded octet. So looking at this, we know that there are 4 bonding regions, 1, 2, 3, 4, around the central atom. So we know that this would be a tetrahedral geometry, right? And as such, we would draw it in a tetrahedral sort of way, right? So we could do something like this, and then draw this out a little bit more, right? And then let's just say this one's coming out at us, right? We'll just call that, and we'll say this one's going back, and I'll put the oxygen there. And so we know, looking at this, we can see that the single bonded oxygen is carrying a negative charge, So there's a tetrahedral conformation, right? So it has an AX4, right? Molecule type, formula type, because there's no lone pairs on the central atom. Tetrahedral geometry, tetrahedral domain. Expanded octets, in other examples, we're going to find that we're going to have more than just 4 domains around a central atom. That's where it gets fun. And then sometimes we have less than that. For instance, things that, like boron and aluminum, they can carry less than 8. They usually chemically sort of balance out closer to 6 valence electrons. So that's a decrease, right? That's less than 8. That's less than the octet rule. You have examples where from like in group 3, one of these days I'm going to figure out how to turn that off without getting in trouble with the district. I'm going to figure it out. Maybe I can convince somebody to, I don't know, adjust the range. That'd be nice, be helpful. Where was I? Oh yeah, like I think I was talking about around group 3 elements. So around, around the silicon area, right? When you get to like right here, sulfur, notice that we had more. So from there down, you can get what are called hybrid orbitals. And that from the third period. From the third period down, you can get what are called hybrid orbitals. And that is another lesson entirely where we talk about orbital hybridization. But essentially what that means is where you see these 2 bonds, we have what is called an overlap, all right, of bonding regions. We have the single bonds are a certain type of bonding orbital, and the double bonds are another type of bonding orbital. And so I have a lesson on hybridization that'll be available for you, and that's where you're going to want to go to watch that. That's a little too entailed for what we're doing here. And then there are times where you can have, we've been looking at pairs, bonding pairs, lone pairs. There are some exceptions to the rule where you have an odd number of electrons. And I know that makes no sense according to everything you've been taught in chemistry so far. But things like nitrogen will sometimes carry an odd number of electrons and still have the best overall lowest formal charge for each atom and the overall molecule. Of course, it affects its polarity. And you just have to know that nitrogen is one of those that's going to do it. And that's really it. It's just a matter of, getting familiar with this. So if you're in my class, there's problem sets for you to be working on. I'm going to have other videos. You're going to want to watch those and just practice and practice and practice. So I hope this helped. Be looking out for another lesson video, and we'll dive into this. It just takes practice with this. We'll be looking at different geometries that go beyond tetrahedral. That's where expanded octet really gets kind of fun, is that once you have more than 4 around the central atom, you have different geometries, and that's where it gets really, really fun. So it's great seeing you again. Thanks for tuning in. Always wonderful and great to learn with you. Go get some coffee. It'll help you understand these whole things about octets, expanded octets, breaking the rules. Good seeing you. Bye.